Hey guys, welcome back. Today we got a lot of connections to make between linear and rotational kinematics concepts, so let's go ahead and get rolling. So angular quantities have kinematic relationships just like our linear quantities. So let's compare. When we talked about linear kinematics back in the fall, we had the following variables. S represented our distance or position, V our velocity, and A our acceleration. And in our rotational unit, the related quantities are theta for how much something has rotated instead of how far something has traveled, omega for how quickly it's rotating, and alpha for how quickly the rotation is changing. So if we look at the linear formulas that we had before, Vf equals V naught plus At, it has a rotational equivalent. Omega F equals omega naught plus alpha T. Notice we just replaced the linear variable V with the rotational variable omega, and the linear A with the rotational equivalent of alpha. Our so vote for AT&T formula has a rotational analog as well. Doesn't sound as cool if we say so vote for alpha TT, but it's still there. In fact, I usually just say the so vote for AT&T formula, but when I write it down in this unit, I'll use thetas and omegas and alphas instead. The no time formula can be transferred over as well, and we'll learn of even more later on when we talk about rotational inertia, the analog to linear mass. So let's begin with a quick video from Wheel of Fortune, and we will calculate what the deceleration of the wheel is.
Nope, no M, and not much time either. That sound means it's running a little short here, so I'll give the wheel a final spin. Ask you to give me a letter from the puzzle at 5 seconds to solve it. Vowels worth nothing. Consonants are going to be worth, well, we'll give one more spin, see what we can do. I'm getting it. It was lifting up that art. It took a lot of energy out of me. That was worth waiting for.
P.
There are two P's.
Yes!
$10,000.
Yes!
What is it?
All right, bonus points for anybody who can solve the puzzle. But let's see if we can calculate then what the angular deceleration of the wheel was. So as it was going, I noticed, I counted off, that it took about 5 seconds or so, maybe 5.5. We'll keep it simple. Let's say it came to a stop in about 5 seconds. So how can we then calculate what alpha is? Well, if you remember what we used to do, we used to make a tower of things that we knew and didn't know, and then pulled out the formula that we needed to answer the question. So we used to do S naught, SF, V naught, VF, A, acceleration, and time. And so if we do the same sort of thing for angular velocities, let's see, we have theta, so the initial angle, and the final angle. We have the initial speed, although that's an omega, not a v, and we have the final velocity. We have the acceleration, or in this case the deceleration of the wheel, and then we've got time. So which of these things do we know? I think we can say the initial angle. Typically we just say that that is 0, and so the final angle, at least in one of the ones where it went from bankrupt to bankrupt again, was a full rotation. Let's work in the standard unit. So one full rotation is equivalent to 2 pi radians. And the initial speed, we don't know what that is. so I'll just leave it blank for now. The final speed, well, it eventually came to a stop, so we'll call that 0. The acceleration, that's what we're trying to find, so that's another variable. And then the time we measured, just by counting, to be roughly 5, certainly with one significant digit. So this particular combination of knowns and unknowns is one of the most difficult ones to work with because we don't know the initial velocity. And each of our formulas, if it has a velocity in it, it has the initial velocity in it. So we're going to have to use two different equations, and let's pull the velocity formula out. That's final velocity equals initial velocity plus acceleration times time. Notice how I still kind of say the same words we did before, but I'm writing the rotational versions of each of those down. And I'm also going to use the so volt for AT&T formula. So that is so, or in this case, tho, plus omega naught t plus 1/2 of alpha times squared. So I've got two equations with two unknowns. That's a system of equations, and we can solve that by substitution. And I'm going to substitute into this formula an expression for omega naught. So if I can get omega naught by itself, perhaps by subtracting alpha t from both sides, I get a formula that omega naught is equal to omega final minus alpha t. And this expression can get substituted in here. And that gives us theta f equals theta naught plus omega f minus alpha t times t. So omega naught, that's this, and then this t transfer down, and then that's still plus 1/2 alpha t squared. And now I know everything in this formula except for alpha. So I can solve this. The final rotation was 2 pi. The initial rotation is 0, so that term cancels out. The final velocity is 0, so that term goes away. But I still got a negative alpha. There's a t and another t, so that's 5 times 5. So I'll write 5 squared. And then here, plus 1/2 of alpha times 5 squared. And I know it's a little sloppy, but we can solve this. This is just a number, 2 pi. I'm going to leave it as 2 pi for now, and when I calculate it, it'll be more exact that way. Let's see, this is negative 25 alpha, and then half of 25, so that's 12.5 alpha. These things can be combined, and that becomes negative 12.5 alpha. And dividing both sides by negative 12.5, we get that alpha must be 0.5026, and since I said we only really have one significant digit in the time, we ought to report our answer with just one significant digit, so we'll say negative 0.5 radians per second squared. Now, a cool follow-up question would be, if we were a contestant, and now that we've studied the wheel and we decide to go play, we ought to be able to figure out, how fast should we spin the wheel initially to get it to land on a specific location. So, one more question. This is kind of made up numbers, but you probably tried to spin a ball on your fingers, and they tend to stay balanced pretty good for a while, but once they slow down to a certain speed, then they topple over. Perhaps that speed is 5 radians per second. I kind of made it up, but what I want to know is if a ball is staying on your finger for 2.5 seconds, and while it's spinning, we counted and saw that it spun a total of 10 times. What was the initial speed that we had to exert on the ball? So let's make a summary of what we know and what we don't know. So we know a couple different things here. First of all, we know that the ball will spin until it reaches a speed of 5 radians per second. So if it starts at like 20, 15, 10, and then once it gets down to 5 radians per second, it's too unstable to spin anymore. And so that would be its final velocity. And some facts, specific facts to this problem were that the ball spun for 2.5 seconds. So that'll be our amount of time. And it spun for a total of 10 times. So if we assume its initial position is 0 radians, then it spun for a total of 10 times 2 pi, or 20 pi radians. And we're looking for the initial speed. And this setup looks oddly familiar. I think we had the exact same setup last time. With this combination of numbers, we are looking for the initial speed, and we don't know acceleration, so I don't want to use the so vote for AT&T formula without acceleration. We also had the average velocity formula, which might be useful here. That didn't have an A in it, so for those of you who forgot, that formula is with the old units, or old symbols, it was the final position is the initial position plus 1/2 of the velocities added together. This quantity is the average speed, because you add the speeds up and you divide by 2, times time. And so if we write the rotational version of this, the final amount of rotation is equal to the initial amount of rotation plus 1/2 times omega naught, which is what we're looking for, plus omega f times time. And we can start filling in some details. This is 20 pi, roughly 60 radians. The initial position, like usual, cancels out and is unnecessary in this problem. We've got a 1/2 times omega naught plus omega f. So omega naught is our variable. Omega f is 5, because that's when it's too unstable to stay spinning anymore. And the amount of time is 2.5 seconds, which doesn't sound like much, but if you ever tried spinning a ball, 2.5 seconds is pretty good. And let's see what we can do. If we multiply both sides by 2, we'll get rid of the 1/2. That gives us 40 pi equals omega naught plus 5 times 2.5. We could distribute, but I'm going to divide both sides by 2.5 instead. So those cancel, and that gives us roughly 50. All right, 50.3 is equal to omega naught plus 5, and subtracting 5 from both sides, and we have an initial speed of 45.3 radians per second. So there's a few examples of how to calculate rotational scenarios by remembering our old linear kinematics formulas. Be sure to tune back soon when we start talking about rotational inertia and how rotational inertia and linear math have a lot of common things, and then we'll ultimately tie everything together by comparing how force and torque are related.